Thank you, Professor Busekin. I'm delighted to be here and to receive such a generous introduction. And I also want to thank the Institute and Miriam Teschel for organizing, and also Marine Roussignol for trying very hard to accommodate the last-minute changes in planning for this event. So, Professor Busekin raised two issues that connect directly with his talk. One is the title, and the other is the interdisciplinary audience. The talk really is represents an interest of mine that goes back many years, and it's different from neuroeconomics. And the original interests were really philosophical and methodological, even though much of the research now is quite technical. And that's an interesting issue in itself. But the original motivation was methodological and philosophical. And to put very simply, the question was, how much truth is there out there in the world, you know? And should we be conservative about the amount of truth, or how do you define the difference between truth and just opinion? And that's a fundamental question for a culture, because there's a broad range of debates we have where it really matters whether we believe there is a true, and I use the word true to mean best, not in a very deep metaphysical sense, but simply where there is generally the community has enough information to generate the best answer, or whether we approach a question by thinking of it really as a discussion of opinions with nothing in the background. And I think there's a tendency in culture always to define truth with respect to procedures. So when we have a procedure for establishing truth, then we're comfortable. But when a procedure is lacking, there is no procedure, then we tend to believe there's no truth. One such procedure, and the one that is in the background of our culture very influential, is a distinction between verifiable and non-verifiable events. Verifiable events are events where, in the end, somehow it will become public what happened, what is the case. And then there are disciplines that deal essentially with non-verifiable events. And you can see I just put two lists. We can put more items on the list. But you have, on your left side, you have the zone of light, and on the right you have the zone of darkness or shade, because you have disciplines where there are many debates, but it's not possible really to prove, or very difficult to prove that you are right. And so we're really going to be discussing the relationship between these two, and are there ways in which we can put some more methodological structure on discussions in the right side. The paper, I'm going to also talk about a very specific paper that supports this. It's a paper that came out this year, and my two co-authors are Sebastian Sung from Princeton, John McCoy, who's a PhD student at MIT. And the paper is interesting. Well, personally, it's interesting, of course. It came out in Nature, and one way to think, what is true? What is true is what's published in Science and Nature, in our culture. That is operational definition. It's either mathematics or it's empirical fact, and if it's an empirical fact, if you get it published in a very small number of journals, then it's defined as true. Otherwise, not so sure. Now, the paper was originally submitted 10 years ago. So this was a paper that was in the review process 10 years at two journals, Science. And the original title was the one you see, okay? That's the original title, which was rejected. And over the years, through probably a dozen referees, we had an interesting internal discussion of what people like and don't like. And it's a shame, actually, that some of these discussions there's no way of making them public, because they are interesting internal debates about what is wrong or what is right. And one of the debates that very clearly came up in the very first Nature review is that what we were presenting was a method that was going to extract and combine opinion about non-verifiable events. And we gave some examples of these events. And I'm going to show you a referee's comment. This is now a referee to this paper a few years ago, where we gave two examples of questions where this particular method might be useful. So the first question was a forecast about what will happen to humanity in 100 years. This is an important question. Will humanity survive by the year 2100? What is the probability? Is it 0? Is it 100%? 20%? 95%? And we said, maybe we can try to get the best probability for this. And the referee said, this is nonsense. There's no such thing as the best probability, okay? A second example, we said, this is example C. This is something that you often see in historical and public and actually debates. A counterfactual question. The use of the atomic weapons at the end of the Second World War, were they necessary or not? Well, it depends on what would have happened if the atomic weapons were not used. And the question then is, how long would the war have continued? Would it have continued for 3 months or 6 months or years? So this is a question, you have books written about this, and we said maybe we can find the best answer to this. Putting a very ambitious goal. And the referee said this question is even more problematic. It is pure counterfactual speculation. By definition, there cannot be a true answer. So this is a natural science attitude that this kind of question belongs in the other departments. It doesn't belong in nature because we deal with real things, okay? And this is fantasy. That's I think the reaction. So, but the question is important. I'm going to give just one. Do I have an example here? No, I don't have an example. An example in economics. Was Keynes right? Economists debate this question. And you can get a Nobel Prize for saying yes. You can get a Nobel Prize for saying no. But is that a verifiable question? So. It's important for our culture to have some method of doing this. And so what does our culture do? Well, it either relies on experts or it relies on algorithms. Now, just to finish the story for us had a happy end because the paper was published. And it actually was on the cover, which is on the right side. And we had actually proposed, what you see on the left is the proposed cover that the author submitted, and it wanted to highlight the question of when you have these issues, who is right? Is the average opinion right? Is the community right? Or is there maybe some expert individual? And what you see in the image on the left, there's a crowd of people looking at a very military painting. It was supposed to be a painting in bad taste, And then on the right, there's a single person looking at the blue donkey, which if I didn't know, but the artist who suggested the blue donkey was German expressionist artist banned by Hitler and so on. So the idea was to suggest that somehow the individual is sometimes, right, and the average opinion is wrong. So that's our problem. How can we I'm just thinking now whether yes, we're in good shape. What do we do with these unverifiable questions? Well, with unverifiable, I'm sorry, I'm going to go back to there's something a little bit mixed up in my sequence. Yes. So if we take stock of where we are from the standpoint of method, with verifiable questions, there's at least a reputational risk in people making a prediction, because they can be proven wrong. So if you make a prediction about the weather, you make a prediction about the stock market, about the political elections, and so on, if you're wrong, there is some cost, and it becomes obvious who is more right and who is more wrong. It's also relatively precise. And there are also methods with verifiable problems that are effective and not democratic. And that's an important issue. We'll keep this issue in the background, whether democratic methods, meaning one person, one vote, are the best. With non-verifiable problems, essentially the way society deals with them is that we assign credentials. People who have PhDs, people who have experts in various ways. These are the people who will tell us the best answer. And the forecasts that people make are fuzzy, and it's difficult to monitor progress. Now, there's been recently an attempt to replace expertise with something called crowd wisdom. And crowd wisdom is an old idea. It essentially says there's more information in the community than there is in a single person. And that is true almost by definition. If you have 100 people, they will have more information than one person. That has to be true. So the more people you can ask, in principle, the better your answer is, the more accurate your answer must be to any question, if you know how to combine information. So the issue then becomes, how do we combine information? And historically, there's an approach which goes back to Condorcet, which is essentially voting. Let's ask people to vote yes, no on different questions. And historically there are two important results, and one by Condorcet, the other by Francis Galton, and they're culturally interesting because Condorcet, in the rationalist style of French intellectual style, he proved a theorem in the late 18th century. It's called Condorcet's jury theorem. And it said that if you have a question, true or false, and each person has more than 50% chance of being right, and people's judgments are independent, if you ask enough people, eventually you are certain mathematically to get the right answer. So this is essentially statistically a law of large numbers. And he proved it, and he collected no data. This was just taken as a theoretical fact. Democracy works, assuming that each person has a 50% or better chance of being right. Okay. Condorcet is not cited very much in this area today. Instead, the person who is cited is Francis Galton. Francis Galton was a famous statistician, British, also very mathematical. He wrote a letter to nature in 1907 that didn't have any mathematics, but it had an experiment. And the experiment was, can a crowd of people correctly estimate the weight of an animal after it's killed? So he went to a country fair in England where people were looking at different cows, oxes, and he asked several hundred to write down what they think will be the amount of meat produced by the animal when it is killed. Okay? And what he reported is that the median estimate was almost exactly right. And this is today this is just the starting point for the whole literature. And the paper was called Vox Populi, which is the voice of the people. And he explicitly presented it as a test of democracy. And the way he wrote, it's a beautiful, very short paper. It's essentially one page of published text. The way he wrote it is that, unfortunately, I have to say democracy works. This is 1900. Democracy was not yet. The House of Lords was still voting. It was just about to lose, in England. He said democracy works, and it works by taking the median estimate. And he said anything except the median is going to be rejected by the majority. So the quote you see here is very political. According to the democratic principle of one vote, one value, the middle estimate expresses the vox populi, every other estimate being condemned as too low or too high. So now, in the last 20 years, this idea has become much more culturally influential, I think in part because of technology. Technology now makes it very easy for people to vote all the time on everything. You know, they will vote on you, on your success. They will vote on me as a professor. Everything, there's voting is going on everywhere all the time. You can vote with your iPhones, with your gadgets. Voting is now becoming a real problem, I think, because so much voting is taking place. But there is a movement associated with crowd wisdom, and manifesto is this book, Wisdom of Crowds, by James Surowiecki. He said large groups of people are smarter than the elite, better at solving problems, and so on. And in the US especially, this is very libertarian. There's a political aspect that, you know, we don't trust the elites, we don't trust people with PhDs. The journals, people should vote on what gets published in scientific journals, that kind of thing. You know, that we don't need elites. So, what I'm going to present today, very briefly, is a new crowd wisdom method that changes one thing. It selects the best answers, not the answer that gets most votes, but the answer that exceeds expectations. Now, I want to thank Professor Busekin for asking me to make this non-technical. And this relates actually to the paper. I said the paper was originally submitted 10 years ago. The first submission was extremely mathematical. And it used information theory, entropy, all sorts of things. Every successive version became less mathematical. The current version has zero mathematics. There are no... And in fact, now I have to say, this is not a stylistic change. The authors did not understand that the idea did not need mathematics. We realized that zero mathematics is needed maybe a year ago, a year and a half ago. And we're very happy. And that went through. But it creates problems, because people think without mathematics it's not true. And I have gotten the requests and emails from a colleague saying, yes, but where is the method, you know? And then I sent back a paragraph of English saying, but it's here in English, very clear. No. And in fact, just this week, another email said, I enjoyed your review paper very much. So the algorithm is that, you know, no equations, this is a review paper, right? I didn't respond yet, I don't know how to respond. So anyway, so it also has to be not just in nature, it has to have mathematics for this. Okay, voting. We start with voting. Voting, democratic voting. It is unfiltered crowd wisdom, meaning people who know and people who don't know have exactly the same influence. And it's very easy to show that average opinion is very, very bad often. And this is just one. I mean, the examples, you can go on the web and find examples, but this is something we did internally, asking what percent of the US budget goes to foreign aid. The average answer is 29%. And there's actually published data on this. It's about, people think about a third goes to other countries. The actual number is less than 1%. Okay? And then there's one also about Syrian refugees. What percent are men of fighting age? About half. Correct answer is about 20%. So there are these things out there, you know, that so voting is not reliable. Now, when we move, so this is, let's think, for non-verifiable things, generally voting, I mean, sometimes you can have, for example, you can have a committee voting, like who decides on the Oscars. It's not everybody, it's a committee. But again, at the end, it's voting. Now, for verifiable events, we're in a much better situation. Because for verifiable events, we have non-democratic methods. A classic example of a non-democratic method is a market. And so out there are such things as prediction markets. Prediction markets allow people to bet on events. And let me just jump ahead to a screen to explain how it works, and we'll return to this in a second. In a prediction market, there's an event. The event we just saw was who was going to win the French election. And if you own a share of a candidate, if that candidate wins, you will get $1 in an American market. And if the candidate loses, you get 0. So that means that the current price, which is between 0 and $1, is the probability, the market estimate of the probability that the person will win. And this is a non-democratic estimate because someone who has information, let's suppose you know that there is a scandal, you are inside the campaign of a candidate and you know that there is a scandal that will kill this candidate, you can bet against this and make the price go down because you are an informed person. So the final probability reflects not a democratic average, but it reflects the consensus weighted by how much money people put on the table. And so this is an example from the French elections. The arrow is, there are two, Fillon and Le Pen. Le Pen is the dark blue line. And this is the time course until the end of the election. But the arrow points when the first round was voted. And so what you see, if you look oops, I guess I can't. Oops, sorry. I thought I could touch no. What you see is Le Pen was rising in the prediction market before the first round. Then she made it into the first round, and then immediately the price went down. Why did the price go down? Because Macron was the opponent. So even though the result was positive, the market immediately pushed her chances very low. So this is, and there are examples. For instance, there's a famous example I don't have here, when the 9/11 attack on the World Trade Towers took place. About 4 or 5 days before, the 4 stocks of the airlines, options on those stocks changed dramatically, completely. So someone had inside information about the attack, was betting against the 4 American airlines that were hit on 9/11. So in this sense, markets can be very sensitive to very special information. I said this is okay. So let me give you just a few more examples of these prediction markets. They're used in business, they're used internally in companies. This is an example for an industry, the Hollywood Stock Exchange. You can buy shares of films that have not yet been produced, and the value of your stock is connected to how much money the film makes in the first month. So again, the idea is that people who know what's happening in the studio, is this working well, is the script good, and so on, they will actually reveal by betting what the chances are for the film. And you can also buy stocks in every actor or actress. It's shocking. You just go alphabetically, thousands of them, and their value is connected to the success of the next 3 movies. So every actor, every day, can go and check their own stock rating. And I've heard, this is again the problem of electronics, becomes addictive. People can be checking themselves, am I doing better today than yesterday? Something like this. Another example, this is my last example, is this is a fantasy market, not real money. I should say also the Hollywood Stock Exchange is a fantasy market. There's no real money, it's just for reputation. This is now, the question is, will we see a living large dinosaur walking around by the year 2050? And you can estimate what the probability is. Currently the probability was around 40%. For some reason it's gone down recently. But I want to focus on the text. And this is now, excuse me?
Who was asked the question?
Anybody. This is anybody. You and I can go and, this is not experts. Anybody who is interested in this. So this is not serious in the sense there's no real money. So I don't know.
It's not the only
So,
Excuse me, can you answer the question? The answer to your question?
what, the dinosaur or no?
How is it
Okay, very good. Yes and no. These are public markets. This is a website. I have no idea who answers these questions. No idea whatsoever. This is also public. This is democratic. Anybody can enter anytime anonymously. You don't know who they are. It's a market.
They can be Russians.
They can be Russians. They can be Russians, yes. So someone who wants to manipulate can manipulate. The question I can answer is, this is also anonymous, anybody. The question I can answer is this one we did. This was done through a Polish company that you send them questions. You give them, it's fairly expensive but fairly good. It costs about $1 per person. And they send questions to people on their iPhone. And you have a lot of information about the people. You know their income, their age. You have fairly good data about each person, and you can say what kind of people you want and so on. And they answer, so this came from a sample, a professional sample. We know who those people are. And they are demographically, representative of US, these people, because we did this. So we asked this. Yeah. I think it's good actually to ask me questions because a lot of things.
As you wish.
No. Please ask me questions. Because some things may not be clear. For example, this was the data we collected, and here we're looking at just public commercial sites. You go on the site, predict it. If you want to check later, predict it, and you get a menu of markets you can play in. So on. Now, what is the limitation of prediction markets? The limitation of prediction markets is that you need a contract. You need a contract. So you see on the left, it says they have to be very precise. What is a dinosaur? And they say a dinosaur has to be at least 200 kilograms with identical size and shape, and it's not a bird. Birds are not dinosaurs. So it's verifiable. This is the verifiability issue. Markets need specific contracts. And questions of interest, non-verifiable questions, do not have contracts. So now we're moving into the non-verifiable domain. Suppose we have this was an issue, came up in a talk that I gave a few months ago when President Trump fired the FBI Director Comey. CNN had a headline, "Why was Comey fired?" And they had 3 hypotheses. Trump did not like Comey. Trump is an agent of the Russians. A third one was something else. But they were not verifiable. And typically, society and experts and governments need answers to non-verifiable questions. They need answers to counterfactual questions, speculations. What is North Korea really? What is the strategy of North Korea, etc. So we need answers to non-verifiable questions, which brings us now to this method. The method is really based on a single principle, and that is that we're going to ask people not just to give an opinion, but also to predict the frequency of opinions in the population that's being sampled. So we're going to ask each person for a vote, forecast, and a prediction of the distribution. And then we're going to compare the votes against predicted votes. And the focus today, there are other things you can do with this data that are very interesting, but the focus today is just on a simple idea. That the best answer is the answer that gets more votes relative to predictions. So the best answer is not the most popular answer, but the answer that is most surprisingly popular, unexpectedly popular. And that's it's an idea that's simple to state, but hard, I can say from personal experience, to really believe. So I will start with an example where it's very clear what's going on, and then we can move on to other things. The example where it's clear what's going on is a simple factual question. And we're going to use this question to demonstrate the logic. It's not a question that is interesting in itself, but it's a question that demonstrates the logic of the approach. The question is a part of a survey that has 50 problems. Each problem corresponds to one state in the United States. So Massachusetts, Pennsylvania, California, New York, and so on. The question is the largest city the administrative capital of the state? And it turns out in about 60% of the cases the answer is no, 40% of the cases the answer is yes.
Your graph is a bit hard to read because it doesn't add up to 100. What was the other answer?
No. Personal votes is actual number of people. So this is a survey with about 30 people. Yes. So this is a question, this question is interesting because it's a question that most people get wrong. It asks whether Philadelphia is the capital of Pennsylvania. And most people in the US believe it is, 2-1, because Philadelphia is a very large city, but also Philadelphia is historically important. It's the city where I think the Declaration of Independence was written and so on. So it has a kind of a quality of an important city, and most people think it's the state capital. Interestingly, there are other, if you go, let's say, California, Los Angeles is the largest city. Nobody thinks Los Angeles is the capital of California. So there's all kinds of interesting intuition people have. Like Los Angeles seems like Hollywood, it's like, it cannot be the capital. I never heard of anything happening in Los Angeles except, movies and so on. So in New York, people know New York is not the capital of the state of New York. So people are drawing on a lot of information. Some information about the size, some information about the cultural knowledge, and so on. So the questions are not so trivial, actually. Okay. But this is a question where they get it wrong. The majority is wrong. So standard approach in the literature to improve on majority opinion is to ask people for confidence. So confidence you can ask subjectively, or you can be precise. You can ask for a probability, saying what is the probability that you are correct? What is the probability that this is the right answer? And it turns out both empirically and theoretically confidence does not guarantee the right answer. So there are two parts. It does not guarantee the right answer empirically, and it does not guarantee the right answer theoretically. Empirically, we can say, well, people are overconfident, but also theoretically, it does not guarantee the right answer, which is a different issue. Empirically, we ask for confidence. So these are the confidences on a distribution. So we ask confidences from 50% to 100%. 50% meaning I'm not confident at all. 100% means I'm certain. And what you see is the distribution of confidence estimates, and they're basically the same. The people who say no, some of them are extremely confident. The people who say yes, some of them are also extremely confident. And generally confidence helps a little bit, but doesn't help very much. Not robustly. Now this other question then is predict what the distribution of answers will be. So here we're plotting the distributions of answers and we're saying predict what percent will agree with your opinion. And you can give an answer from 0 to 100%. 0 means nobody will agree with me. 100% everybody will agree with me. And what you find that people who think that Philadelphia is the capital think that most people will agree with them. People who think Philadelphia is not the capital think they will be in the minority. Okay? That's the robust empirical finding. Now, important thing here now, whenever I present this, and when we see this, we have a tendency to laugh and to say, well, laugh at the people who say yes, right? Because they think they have the wrong answer, they're confident, and they think other people will agree. Okay? It's easy to laugh. But I don't think they're stupid. I don't think they're stupid. You know, they are saying, look, it's possible it's not the capital, but not very likely. And, you know, why would anyone say it's not the capital? Right? I think surely people are making mistakes, but basically this is according to Bayesian theory, you know, what you see here. So what do we do then? What we say is we're discounting the votes by predictions. And predicted votes here are less, the correct answer of course is no, but if you look at the predicted percent that vote for no, it's going to be less than a third. Because the people up here are confident that everybody's going to vote yes. So what happens is no gets 30% of the votes, but is predicted to get only 20%, and because it does better than predicted, the algorithm says no is the right answer. So you're essentially imposing a handicap. You're saying you have to handicap votes relative to predictions. And the handicap is set by what people, you're asking the crowd to predict the crowd voting outcome, basically. That's the claim.
Did you ask also then what's their prediction of confidence of others?
Yes, we did.
Okay.
Yes, we did.
Can you repeat the question?
Yes, I'm sorry. The question was, did we ask them to predict also the distribution of confidence? And we did. And now that's a fairly difficult question to ask, but in this particular survey we did. And that's a useful question if you want the method to produce not a binary answer, whether it's better to say yes or no, but to give a probability. Because if you want to push the method to identify the optimal probability, collective probability, then you're really dealing what's in principle a multiple choice question. Is the best probability 100%, 95%, 90%, 85%? So the structure of the question then really becomes a categorical probability scale. And to apply the method there, you need to get people's estimates of what will be the probabilities that others will give. So what you're asking really is, did we ask people to give a probability distribution over the probabilities that people will say? That's essentially. Now, I don't have any analysis of this in the talk here. But one thing I can say in practice, those are difficult questions to ask. And we're not sure how well people understand what we're asking. Because here, now you're asking me, it's a danger of asking because the long answer will be long. But here, the issue is, what is the concept of the best collective probability? What is the best probability, let's say, in a group of people for something? Here, the best probability is either 0 or 1, because if you ask 1,000 people in the US, surely there's information that proves that Philadelphia is the capital or is not the capital. Someone knows, right? So the best collective probability must be 0 or 1. But if you go back to questions, we saw a little bit before, like, why was Comey fired? The best probability may be 70%, the best collective probability, because there's not enough information. So you're really searching then for a number, not a 0-1 value. And then you need to ask for confidence and also to people to predict the confidences of others. That's it. Now, this is I said earlier, at least for questions with two answers, we don't need any mathematics to make the argument for the method. And this may be, but in some sense, this is the most difficult part of the talk, right, this slide here. And this is the part that I say we didn't understand this until a year or two ago, although we worked on it for more than 10 years. The logic for why the best answer is the answer that is more popular than expected. So let's think about this from the perspective of one person. I don't know if Philadelphia is the state capital, but I can think hypothetically. I can ask myself, if Philadelphia is the capital, so there are two possible worlds. Philadelphia is the capital or it's not the capital. Let me think about those two possible worlds. This may seem strange because there's only one world, but this is, in statistics, there's hypothesis 1, hypothesis 2. This is something very basic in Bayesian statistics, 2 hypotheses. What should I observe if Philadelphia is the capital? Well, Philadelphia is the capital. Probably everybody thinks that it is. Why? Because why would anyone think it's not? The scenario for someone to think it's not the capital, when it is the capital, is pretty unusual. It must be someone got confused about something, okay? Now, suppose if Philadelphia... so I'm a person who doesn't know the right answer, but I'm thinking hypothetically here. If Philadelphia is not the capital, then of course, fewer people will believe it. Now, I don't know how many, but it's going to be less than 90. It's going to be something like 60%. But it doesn't matter what number I put here. All it matters is that it's less than 90%. Now, 1 and 2, you don't have to believe, but to disbelieve 1 and 2, you must disbelieve that God is very bad and is actually getting us to believe, more people to believe something if it's not true. Okay? Which is possible, but very unusual. So now step 3, I'm being asked to predict how many people believe that Philadelphia is the capital. Well, if I believe 1 and 2, my prediction must be between 60 and 90%. Because if it's one way, it's 60%. If it's the other way, it's 90%. And since I don't know which hypothesis is true, the expected answer must be in between 60 and 90. Again, it doesn't matter exactly where, but let's say I put it at 80. But the important thing is only that it's in between 60 and 90. Okay? Now, if I collect data and I find 90%, which is bigger than 80%, then yes, must be the true world, the right scenario. And if I find 60%, which is less than 80 that I predicted, then it must be that I'm in the no world. Okay? So by putting down 80% as the prediction, I'm saying if I get bigger than 80, I'll say yes. If I get less than 80, I'll say no. And that's the logic of the approach, essentially, from the perspective of one person. And the method really then just averages over many people. Now there's a lot of noise, a lot of other stuff, but that's the essential idea.
Why you say that you don't need mathematics? I mean, you can make the proof mathematically, I guess. You can. So the only when I say you don't need mathematics is that you can do it this way. With the proof is for binary things?
Yes. To go for more than binary, you need mathematics in a very serious way. Yes, that's true. But I think this is useful because here you can see that there are some big assumptions here. There are assumptions. There are assumptions that people can think hypothetically, that they're thinking hypothetically. I'm sure they're making all kinds of mistakes. There's all kinds of psychology. There's big psychological assumptions here. So I will give one more illustration, and then we can stop. The illustration is I will skip a little bit of data from applications and go to a study that was also in the paper, which used the domain of modern art. And now with modern art, or with art in general, there are two questions. One is, of course, the aesthetic value, subjective value, a genuine value in some non-financial sense. And then there's also just purely a question of how much is this selling today. So in the experiment, we collected both types of information, but we were interested whether people can judge the market value of modern art. And, yeah.
May I ask you to go back?
Sure.
I'm not sure.
To this one here?
To the conclusion that the surprisingly popular answer is correct.
Mm-hmm.
And then how do you link it with the previous example?
The previous example, what the previous example showed is that Ah, yes, very good question.
You mean those who say it's not the capital, but I'm sure the crowd is.
Well,
they
so
all say
Can you
yes.
just again repeat the question?
yeah, very good. The question is this syllogistic proof is a little bit different from the way the data was presented in the previous slide, and the question has to explain the relationship between. In the previous slide, so let me just change one thing. If Philadelphia is the capital, imagine you're a person who believes that Philadelphia is the capital, then you will believe that most people will agree with you because you think number one is the likely scenario, and in that scenario it's 90%. Now you may not be sure, but you might say probably 85% probability that people will agree with me. 85% will agree with me. If you believe that number two is the more likely answer, if you believe that Philadelphia is not the capital, then you think that about 60% will say yes. That means that only 40% will agree with you. So you expect to be in the minority. You expect that most people will not agree with you. And what we saw on this slide before is that people who say no, think about maybe 30-40% will agree with them. This is the, I don't have a pointer, but if you go vertically from here, the average estimate of how many people will agree with them is about 30%. So they expect to be in the minority.
But what is surprisingly popular here?
The surprisingly popular answer is no. It's not obvious from the picture. I have to apologize. To prove that the surprisingly popular answer is no, you would have to average all of these predictions, and you would have to compute the average prediction of votes for no. And you could use the data. You could use the data on those two slides on the right to compute the average predicted votes for no. And you would find that the average predicted votes for no are about 25%. But the average votes, but the votes for no are about 35%. So no is surprisingly popular. You see? So you're right.
So surprisingly popular means actual versus predicted.
Yes, correct.
Okay.
Yes. And this was not clear from this slide. Surprisingly popular means actual bigger than predicted.
Okay.
Exactly. So this only exposes how a very rational person might think about this. But actual meaning better than predicted. Okay. So looking now at this art, I think the interesting thing about this experiment is that we asked both experts and non-experts. So the experts are people who are gallery staff or owners of small galleries in Boston, in Newbury Street.
Does it mean that you could somehow, with some assumptions, separate the gathering of the votes and the gathering of the prediction, like using prediction market to get the predicted yes from other people, and then having the vote in the report,
yes.
Like, because if you look at Le Pen, for instance, forecast in the prediction market in the UK,
yes,
you could see that the probability of the value for the first round of the election was fairly too high.
Mm-hmm.
And it was the same for the Austrian elections. They were wrong as well. There are many examples where they are wrong, as we say. So it means that you have, from another population, so there is a problem of the pocket, I mean the conditional of the budget constraint, but you could have predicted votes in the prediction market, observe votes, and then do something about this, like answer a question on political.
Yes, although in a standard prediction market you would need the event. So I'm not sure whether you're thinking of. You can run a prediction market on what the votes will be in a poll. That's.
Because we
yes.
did it for another purpose.
Yes.
Hypothetical things, like when you ask people what is the value of this natural park.
Yes, that's right.
And then you don't have a verifiable answer.
Yes. That's right. So this is a question kind of deeply connected with with the research direction, and it's true that I think in the background of your question is also an issue of incentives. That you can, this is a method you can put incentives on, so that people are not trying to sabotage or disturb, strategically the answer. And one could say, for example, can someone try to, if I want the vote to come out yes or no, maybe I make a very low prediction to make it be surprisingly popular. So you have to worry about incentives and things like that. There's a separate question of whether this can be made dynamic, because prediction markets are beautiful because they're dynamic, because every minute you see some change. This is static. This is a pole. So how to make this dynamic is an interesting question, but not very easy, I think. So that's. But back to the experiment. So what is the truth here? The truth is defined as market value. It's not what's really good, whatever its market value. So we'll just show some examples. There are 90 paintings. They range in value from $50 to close to 50 million. So it's a logarithmic distribution, scale of logarithmic values. And this is, yes.
Did you tell people the name of the artist who made the painting?
Yes. No. Yes, the question is, did we tell people the name of the artists and so on? We did not tell them the name of the artist. We gave them very high quality, this was a physical book. It cost $50 each book to produce with glossy paper. We gave them the technique, the dimensions. So if it was acrylic or whatever, the dimensions, so essentially physical information plus the visual, but no information about date or artist. They may have been told that it's all 20th century art. That's it. Yes?
Verifying the value, did you look at when the painting was last purchased or sold?
Yes, we went for when, so there's very different types of information, because some of them are just solo websites where an artist says, you can buy this for $100 or $1,000. And then for the big ones, we went to the last sale, the most recent sale. And in fact, some of the major items now are worth much more than at the time of the experiment. So, but we went for the last sale.
But did the range of sales say over 6 months or 10 years? Because some famous paintings don't sell frequently. And so if you look at it 10 years ago,
Yes.
that's the market value, that might not tell you what the market value is today.
That's true. I mean, essentially here, when we analyzed the data, here we just looked at a very simple question, which is the painting worth more than $30,000 or less? So the way I'm going to present the data here is just a binary question. Can the panel decide correctly whether it's above a 30,000 or below? But the distribution, the way we asked the question is we gave them a 4-point scale. A lowest scale is less than 1,000. Second lowest is between 1,000 and 30,000. Next is between 30,000 and 1 million. And the top is above 1 million. So they basically asked to give a categorical answer. So, if it's, let's say, I don't know, a Picasso, you put it in the above 1 million. So the issue about, it's a really categorical judgment that we're analyzing here. We didn't give them precise, but I should say something. We also asked them for whether they like it or not. And now we have an algorithm for judging the value of modern art. And the algorithm is this. If you want to invest, here it is. The best linear predictor of the value has 2 variables. One is what experts think is the value. 2 is how much non-experts dislike it. As strong, how much non-experts dislike it, okay? So if you have a modern artist, ask, how much people dislike it. That's a robust predictor of in a linear regression. Okay, this is the next one. I'm not going to ask any predictions. That's... Now, I have to say personally, I maybe knew 3 or 4 of the artists from 90. So most of the artists, to an average educated person, are not known here. Okay? I think these are different artists, and they're both worth... and the one on the left, Christopher Wool, now the New Yorker article. New Yorker had a piece on him as the most significant American artist of the 20th century. Now he's selling into the $20, $30 million range. Things. So that's on the right is a very, very hot Chinese artist from China, and the left is a Klimt imitation, professional quality but imitation. So, and this is now my final data slide. We're looking. Here's what we're looking at. We're just looking at experts here, not non-experts. By the way, it's a shame I don't have non-experts. It turns out experts, well, we'll see from the data. So what are we plotting? This will take a few minutes just to understand, but it's a very important slide, and then we're done. We're plotting on the x-axis the actual market value of a painting. You see the scale is logarithmic. So we're going from $50 at the end to tens of millions of dollars to the right. What we're plotting on the right is the probability. So let's look first at the thin lines, just the lines that are barely visible on the figure. Each line is a single expert. It's the performance of a single expert. And performance is given as the probability that the expert will say it's worth more than $30,000 as a function of actual market value. So when the line goes up, it means the expert has some knowledge. When the line is flat, the expert has no knowledge. So you see there's at least few people near the bottom, like here, these right here, who know nothing, essentially. But they're working in galleries, okay? But most people know something, so that's fine. But the other thing you see is that most of the lines are too low. What does it mean too low? That they are very conservative. People don't want to say that something is worth more than $30,000. If the line is not biased, it would go through this red dot. This red dot is the point where a painting that's worth, this is a painting that's worth $30,000. I don't know if you can see this. This is a $30,000 point. And that painting should have a 50-50 chance of being rated above 30 or below 30 because it's right at the boundary. So the curve, the performance curve, should go through that red diamond. But in fact, a painting that's worth $30,000, most of the lines here, most people are much less than 50% likely to say it's worth more than, most people will say it's worth less than $30,000. So essentially, most people are conservative in making judgments of value. Now, what happens when you average majority opinion? If you take individuals and compute majority opinion, the decision of the collective, majority opinion becomes even more conservative. If each individual is conservative, but has a conservative bias like this, the community will have a conservative bias like this. Because it's going to be very unlikely for any painting to have more than 50% of the experts saying it's worth more than $30,000. So you have a small individual bias amplified into a big community bias. The crucial thing is that nobody is making a mistake here. If you're an individual and you're looking at paintings and you're looking at something like this, you've never seen this before, why should you guess? It's more likely that it's not worth very much. That's the base rate. If you don't know anything, you go by average statistics. Most paintings are not worth very much. And therefore you should be conservative. And being conservative is perfectly rational for an individual, but at the collective level it's irrational, because that base rate information gets multiplied every time. And the person who recognizes, says, this is, I know this artist, that's just one vote. And you have all the other people who don't recognize it, who are legitimately saying that it's not worth very much. So majority opinion is biased against anything that's new, unusual. If you're evaluating grant proposals, if you're sitting on a panel, they are very conservative. They're conservative by algorithm. It's not that people are conservative, but the method is conservative. Because if you have something that's very interesting and new, and you have 10 people in the jury, 3 recognize it, 7 don't recognize it, and they're all voting 1, 2, 3, 4, 5, the ones who don't recognize it will win. It's not because they're bad, it's simply because that's the nature of the majority method. The algorithm is biased, even if the individuals are not. So you need to debias, and the green line is the surprisingly popular algorithm. And you can see that what it says essentially is that if we take a panel and we're interested in whether its painting is worth more than 30,000, we don't need 50% to say yes, we only need 20% to say yes. If 25% say yes, then the answer is yes. Okay? We are handicapping the yes votes and giving them more weight. So I'm going to, question?
Yes. So you have for each prize, so you have a distribution of opinions.
Yes.
So majority voting is the median, average is the mean, and my question is, how is surprisingly popular related to like other moments of the distribution? It has to do with the extreme compared to the mean.
Well, here we're converting. This is really a continuous forecast problem, but we're converting it to a binary question, saying, is this just worth more than 30,000? And so majority opinion would give you the same answer as going by the median, if you think about it. And what we're really doing is we're reweighting the median. One way to think of it, because we're in the continuous setting, the surprisingly popular principle is a median, but giving different weights to votes above and votes below. That's what it's essentially doing.
Is it like taking the quantile 20% or something like that?
Well, it's excuse me? Yeah. So the question was, I'm sorry, I didn't repeat the question, but the question was, I think to explain a little bit more the relationship between what is a continuous, because each person has a continuous estimate of what the value is, and how this, so I think for this talk, I'm really just, in fact, the paper itself is really just, apart from the appendix, but the paper is really just about binary questions. So we're saying, let's just look at a binary question. Is the painting above a 30,000 or not? So this could be a question that someone says, I want to sell this to you for 30,000. Okay? What are you faced with then? You're faced with a question, is it worth more or less? And now you're going to ask 20 people, and then you're going to make a decision. So that's the situation. And I'm saying, if you go by their average opinion, you're going to be too conservative. That's it. Okay. And my just to finish up, my last slide, and then is going back to what I started with, that I think there are better ways to aggregate than majority opinion, and that the distinction between verifiable and non-verifiable content is not where the boundary is not as sharp and is not where we think it is.